All right, so these last two properties here are probably two of the more important ones, especially for this particular module, because we're going to use these to transform our capacitors and our inductors into the S domain. Okay, so let's take a close look at time differentiation. This is kind of what I was talking about at the beginning of the module when I talked about how the Laplace transform can basically turn differential equations or calculus into algebraic equations and simple algebra. And so we see that here in the time differentiation property. So what it's saying is that originally, again, let's say we had some function f of t that has some Laplace transform, f of s. If instead we take the Laplace transform of the derivative of f of t, right, df of t dt, this is equivalent to doing two things in the S domain. The first thing is we're multiplying by S in the S domain. So just straight up S times f of s. So if my original function had a Laplace transform of f of s, my derivative has a Laplace transform of s times f of s. And then the second thing that we have to do is subtract the initial conditions from f of s. So here, if my function of t had some f of 0 minus, let's just say equals a, then I would have to subtract that from my s times f of s. But this scales to higher derivatives as well. So taking the first derivative basically results in multiplication minus a constant. Taking the second derivative results in multiplying by s squared minus s times our initial condition minus the derivative of our initial condition. And so this is basically a quadratic equation here coming into the S domain when we take the second derivative of our function and then take the Laplace transform of that. And so this is showing that we can basically take differential equations and convert them into algebraic equations, right? This went from a derivative into a simple multiplication minus a constant. This went from a second derivative into a quadratic expression. And so this is how Laplace transforms convert algebra or calculus into algebra and make our lives easy when solving these circuits, okay? And so the second basically the inverse of that time differentiation is time integration, which says that integrating f of t in the time domain is equivalent to dividing by s in the s domain. So we basically just saw that f of t has a Laplace transform of f of s, df of t dt has a Laplace transform of s times f of s, and then of course we have to subtract the initial condition. And then we're saying that the integral of f of t has a transform of 1 over s times f of s. So when we go take the Laplace transform of the derivative, we multiply by s. When we take the Laplace transform of an integral, we divide by s. Okay, so those are the Laplace transform properties. I'm going to show you the Laplace transform properties table really quickly. And so you can kind of see all of these properties listed here. There's other properties like linearity, which basically say that we can take the Laplace transform of two terms that are summed together separately, right? A constant, multiplying by a constant in the time domain is the same thing as multiplying by a constant in the S domain. If we have two functions being summed together in the time domain, their Laplace transforms are also summed together in the S domain. We just saw time shifting, time scaling, frequency shifting, first and second derivatives, and integrals. And then there's a couple extra properties down here, but you can basically reference this entire table anytime that you need to see anything having to do with a Laplace transform property, or if you have any questions about any of these properties, the table is probably a good place to reference. Okay, so I'm going to go ahead and end this video. In the next video, we're going to take a look at Laplace transform pairs, and then we will wrap up this section.